All right, guys. Hey, welcome to Quantum Mechanics, Quantum Mechanics 2. This is Dr. Jackson coming to you live from New York City. So I'm recording these lectures in my apartment in the East Village. So at any time there could be gunshots, ambulance sirens, whatnot. So don't be alarmed. I'm well shielded from any harm doing. So, like I was saying in the email, for the first month, maybe month and a half, we're going to have to do these video lectures, just because I'm, having to attend this workshop. It's for reasons that are kind of beyond my control, and I'll be happy to talk about them when I get back. But in any case, we'll make the best of it. The lectures will still be same material. I mean, the good thing is you'll be able to stop it anytime you want. You can watch the lectures in your pajamas. You can stop and rewind and say, "Oh my God, did he just say what I thought he said?" So all that stuff. And as usual, the notes will be in the Dropbox. And yeah, so let's just make the best of it. And if you ever have any questions or concerns or comments, please let me know. Okay, and we'll take care of it. All right. So as usual, what I'm going to do is start with the syllabus, and like I said in the email, I'm going to try to keep these videos to about the 25 to 30 minute range, because that's what I figure I typically the lecture consists of once I get there, which is usually about 10 minutes late, and once I get set up, and hopefully cutting out all my stupid stories and jokes and stuff like that, probably boils down to about 25 or 30 minutes. So I'll try to keep these videos to that length, and it'll still be covering the same material. Okay. All right. So let's go over the syllabus real quick. So obviously this is Quantum Mechanics 2. If you've stumbled upon this video on YouTube by accident, you probably want to shut your computer off and throw it away. No, I'm just kidding. But so this is the syllabus. We're in Quantum 2. You guys know where my office is. It doesn't matter. I won't be there. You know my phone number, but you don't have to call me, because I don't even know if the phone's even hooked up. And if it is, I don't know how to answer the messages. So best way to reach me is email. And as I said in that email a couple of days ago, I mean, you can reach me at my school email, but for whatever reason, I can't link it to my email here on the Mac. And so I have to go on the actual website to check the email. And I just, honestly, I just completely forget most days. So reach me at my Gmail account, because that's I always have open, and that's on my phone. And so that's the best bet. Okay. Office hours. So that's going to be kind of interesting for the next month or month and a half, because this workshop keeps me busy from 9 o'clock your time until probably about 8 o'clock, 7 or 8 o'clock at night your time. So it's long days, and I don't have many breaks during those days. So it kind of sounds like I'm in prison, but I'm not in prison. Okay, I swear. But so I think the best thing to do is just, when you have questions, contact me, and we can set up. If we need to talk, if it's not something I can answer over email, we can chat over Skype or FaceTime or whatever. Maybe if need be, we could set up Google Hangout or something like that, and we can all join in and talk. But it would have to be in the evening. Okay. So the official time and place of our class meetings is in Science Hall, 205. Don't go there. Nobody will be there to let you in. Just watch these videos from home. And my son's texting me that something sucks. Okay. Um, uh, Now I lost my train of thought. Okay, so like I said, watch these videos anytime you want, and just let me know if you have questions. Okay. Um, so the description of this course. Okay, so as I had talked about a couple times last semester, this is where things are going to get interesting. Okay, so this is the part of quantum mechanics, at least the graduate level quantum mechanics, where we have to put our big boy and big girl pants on, because we're going to start stepping out into the real world where problems aren't always exactly solvable. Okay, so we're going to start by talking about approximation methods, like the variational method, perturbation theory, time-dependent perturbation theory, um, degenerate perturbation theory, all the different types of perturbation theory. Okay. And that'll take up a good chunk of the semester, but it'll lead us into another big topic, which is scattering theory. Okay. And we'll spend a lot of time on scattering theory. We'll spend a little bit of time talking about identical particles, and then we'll end up the semester with a couple week, you know, talking about relativistic quantum mechanics. Okay, for a couple weeks. In other words, the Dirac equation. Okay, so that's meant to get you up to speed so that when you sign up for QFT, you're ready to roll. Okay, you're ready to hit the ground running, because we'll see that relativistic quantum mechanics is not completely satisfactory, and you need something else, and that something else is quantum field theory. Okay. All right. So as far as textbooks go, we'll be using same textbooks that I used last semester or your first semester of quantum mechanics. So it'll be mainly, well, it used to be mainly from Sakurai, but over the years, I've kind of moved away from Sakurai towards some of these other books like Shankar, um, and what Leibov. You guys know I like Leibov, and it's always good, if you're rusty on basics, to go back to Griffiths, because he's got the most concise explanations, for simple topics. Okay. Some of these other, like Merzbacher, I would just cross it off your list. Don't even worry about Merzbacher. But things like Landau Lifshitz or even the Dirac book are really good to go and see, some of how the masters of quantum mechanics explain things and how they thought about things, particularly when we get to scattering theory, which can get complicated pretty quickly. Okay, major assignments. So homework. So I'll try to, again, like I've done for your, or like last semester, I'll try to have about one homework per week. It probably won't be that many. Um, There'll be, like I said, there'll be like bite-sized, homework assignments with 3 or 4 problems, just to kind of keep you, meant to keep you in line with the lectures. And if everybody turns, well, you don't really have a choice. But if you turn your homework in on time, I'll try to make the solutions available after the due date. That is assuming that I actually do the homework. Just kidding. I always do the homework. So late submissions aren't allowed. Okay, but that's okay, because there'll be so many that I'll drop a couple, and everybody be hunky dory. Okay. There is one thing that I like to do in the second half of quantum, which I've done in the past, and that's require people to type up their homework, whether it be in LaTeX or using word processing, Word or whatever. But I highly recommend LaTeX. Okay, so as a trade-off for me not being there, I'm not going to require you to actually do this, actually type these things up. But I would really like it if you would do it. Okay, I'll just leave it at that. But because, well, I mean, for one thing, to turn in the homeworks, you're going to have to at least scan them. Okay, so maybe it'll save you some time scanning if you just type them up. Okay, and the reason I do this is because this might be one of your last major, one of your last graduate level courses, and nobody really ever teaches you or has a course on how to write papers, right? How to present your solutions to problems, whether they be experimental or theory. You always kind of have to learn it on the fly. And so I've done this in the past just because I thought it'd be a great opportunity for you guys to practice those skills, because you need those skills when you go out into the real world. Okay, so not only doing the actual experiment or doing the actual calculation, but how are you going to present this to your audience? Okay, and so that's if you spend the time to start to learn LaTeX and type these things up and turn them in, I overlook typos and things like that, so I'll be a little more lenient on you if you do use LaTeX. Okay, so maybe that's motivation just in itself. Okay, attendance. Well, attendance doesn't really. I guess attendance is just watching the videos. Okay, so I'll keep a close eye on the number of views of the videos, and I'll trace them back. And no, I'm just kidding. I won't do that. But we're on the honor system here, so please watch the videos. I'll try to put them up the night before our scheduled meeting time, so you guys can watch them anytime you want. Okay, and I'll have a separate YouTube channel that'll just have our videos there. Okay. Well, you don't have any, so that usually I say, if you miss class, to check the Dropbox or whatever, but you have no excuses now. You can watch these lectures anytime you want. Okay. All right. And the homework, or the grading policy, is what it's always been. So it's I always weight the homework, even though it says here 30, 35, 35. You guys know I always weight the homework more. Okay. I always put more weight in the homework than I do the exams. And the exams, both the midterm and the final, will be of the qualitative type. So they'll be, the fill in the blank, the multiple choice, writing short descriptions, those kind of questions, because I want you guys, again, to be able to explain topics, not only solve problems. Okay, because 5 years down the road, you're not going to remember a damn thing about the variational method, or at least how to apply it. But maybe if somebody asks you, you'll be able to say, "Oh, variational method, that's, yeah," and explain it in everyday words that somebody can understand. Okay. So that's it. Okay, so the rest of the stuff is the drop policy and all that stuff. I'll put this in the Dropbox as usual, and if you have questions about it, just let me know. Okay. All right. So, right. Okay. So let's start with by talking about the variational method. Okay. So, like I said, up until this point, in your quantum mechanics lives, you've always dealt with problems that were exactly solvable. Might have been really hard to solve, as we saw last semester with certain problems and certain approaches. They can get very technical and very hard, but at least they are solvable, right? You can always go to your mathematician friend and say, "Hey, solve this equation for me," okay? If you don't feel like doing it yourself, okay? But there are circumstances in there, and it turns out that almost every real world problem that you try to solve using quantum mechanics is not exactly solvable. Okay, and so now what we want to do is ask ourselves, well, what do we do? How do we solve problems that aren't solvable? So, as I see it, you basically have two choices. It's a fork in the road, right? So you either just give up, quit, and become biologist or something, right? Just completely give up on trying to solve these problems, which is, I don't accept, right? Or we can try to solve the Schrodinger equation using approximations. Okay, so trying to solve it approximately using certain tricks or methods. Okay, so obviously you're in quantum mechanics too. You've made it this far in your grad school career that you don't want to quit and become a biologist, because what kind of job are you going to get with biology degree? But obviously, you want to try to solve this problem. Okay, and so we're going to try to solve these situations, or try to solve the Schrodinger equation for these situations by using approximations. Okay, and when I say we're going to solve by using approximations, what do I mean? Do I mean that we're going to be approximating the Hamiltonian? We're going to be approximating or we're going to be approximating the solutions, like the eigenvalues or the eigenfunctions of a Hamiltonian that we know? Or are we going to be approximating all three? Well, turns out that we're going to assume, and this is almost always the case in the real world, that we know what the Hamiltonian is, right? Whether it's a particle in some type of field, we know the form of the kinetic energy, and we're going to assume that we know the form of the potential energy. Okay, and so the Hamiltonian is always going to take the form that we're used to. All right, so it's going to consist of the kinetic term, and it's going to consist of some potential energy term. Now, 99 cases out of 100, the unsolvable part, the part that makes the problem unsolvable, is going to be coming from the potential. Okay, and it's going to be in the, we're going to have two types of situations. Okay, so we're going to have the first type of situation we're going to have is where the potential is of a form that has some piece of it that we know the solution for. Right, so it could be like a particle in a box, right, where the potential is zero, except at the boundaries where it goes to infinity, or maybe it's in a simple harmonic oscillator potential, or the Coulomb potential, or something like that, right? But added onto this is some small piece, right? So, and it's that small piece that makes the problem unsolvable. Okay, so here are a couple of examples, and you're going to have to try to work around my handwriting here and all the mistakes that I usually make when I'm handwriting notes. But this is a couple of examples. Like we might have a Coulomb potential, right? So this would be what I would call the simple piece, right? The simple piece meaning that we know how to solve Schrodinger's equation when the potential looks like this, right? But say we, perturb the field a little bit, or we do something to our case where now the potential is not only this, but it has some other function that's a function of space, and we parameterize it by some small parameter. Okay, and we'll see how that parameter comes into play later on when we talk about perturbation theory. Okay, and this is another case. So this would be the case where you have a simple harmonic oscillator potential, and so you turn on some other spatially dependent potential, and now the full potential, looks like this, and the assumption, or the fact of life is that we don't know how to solve these problems exactly. Okay. All right. So that's one situation where we have a Hamiltonian that comes in two pieces: a simple piece that we know the solution for, and a small piece. Okay, and it's that small piece that we're going to use perturbation theory on to try to approximate solutions. Okay, on top of what I would call the simple solutions. Okay, so that's one case. All right, the other case is where we have a Hamiltonian that is just too complicated to solve. Period. Right, and what do I mean by that? I mean that it doesn't come in this nice little simple plus small piece. I mean, here in this case, it's coming in a form that we can't break it into those two pieces and then do perturbation theory, which we'll learn about later on. But this is just, we don't have anything to go on here. right? We don't have any similar Hamiltonian that we can use an analogy or anything like that. And so the question is, what do we do in these situations? Because these situations do arise in the real world. Okay. And actually, what I want to do, I used to cover perturbation theory first, and then um, cover this case, the second case, after that. But actually, it's kind of counterintuitive, but this situation number 2 is actually easier to solve. Okay, the case where you have no similar Hamiltonians to go from is actually simpler to solve, and that's what I've done now in these lectures over the past few years is change the order around and talk about this situation first as a lead-in to perturbation theory, which can get complicated. Okay, so let's ask ourselves, what do we do in cases where we don't know how to solve the problem, right? So we're given this Hamiltonian and I don't even know where to start. Okay, we go to our math friends and they tell us to get the hell out of their offices, right? So what do we do when we have a problem that we can't solve? Well, you could go to the internet. Okay, that's typically what I do when I have a problem that I can't solve, but that's not going to help us in this case. Okay, the other thing we can do is what I used to call Jackson's rule of thumb or Jackson's theorem, but now it's been promoted to a law. It's Jackson's first law, and it says, when in doubt, guess. Okay? And so what we're going to do in order to try to solve these situations where we have these really complicated or exactly or Hamiltonians that aren't exactly solvable, we're going to try to guess a solution. Okay? And it might sound simple, it might sound stupid, but you're going to see that it's incredibly accurate, especially when you're trying to predict the, say, ground state energy of a system. Okay, and I'm going to tell you, and this is why I chose it to come before perturbation theory, is that this method that's called the variational method is so simple that I call it quantum mechanics for dummies, because even chemists can do this. Okay, so if chemists can do this, I know you guys can. Okay, and that was a joke. Okay, so don't tell any chemist that I said that. Oh crap! And I just realized this is being recorded. Okay, anyways, so like I said, this is what we're going to study here is called the variational method, and I'm going to try to describe it, and we'll see how it works, and we'll try to apply it to a few cases. Okay. So what I want to do is use the variational method. So the variational method is basically used to estimate energies. Okay, and in its simplest form, physicist or chemist or whoever use it to estimate the ground state energy of a system. Okay, you can use it to estimate higher level energies. We're not going to do that, but I'll point you in the direction if you're interested to see how to do that. Okay, so our problem is this: we want to solve the Schrodinger equation, which takes the normal form, and we want to solve it for the ground state energy. Okay, and when this is a situation, like we said, that the Hamiltonian is of a form where exact solutions aren't obtainable for the wave function. Okay, and so what we're going to do, the way the variational method works, is we're going to try to guess. We're going to try to guess the ground state. Well, we're not going to really try to guess the ground state energy. We're going to try to compute the ground state energy from a guess of the wave function or the trial ket. Okay, so in this case, we're going to work with a ket, and we call it a trial ket. It's really just a guess. Okay, so it's a guess of what the true ground state ket is. So anytime you see a ket or a wave function that doesn't have a twiddle on it, that's the exact ground state ket or wave function. Okay, and these little twiddles denote our guesses, our trial kets. Okay. All right. And, we've talked about this before. When you're making choices like this, you want to choose wisely. Okay. So we want to use kind of our quantum mechanical intuition here. In other words, we want to, don't just pick a wave function or a ket out of a hat. We want to use our, what we know about quantum mechanics and, what we know about wave functions and things like that, and try to use that in our guesses, right? And we'll also use symmetries of the Hamiltonian, anything at our disposal. We'll try to put that into our guess, okay? Before we go off and solve particular problems, there's a cool little theorem about the variational method, right? And it tells us something about our guesses as far as ground state energy goes, okay? And it turns out that this theorem that we'll prove is true irregardless of the form of our guess or the form of the Hamiltonian or anything. Okay, it's always true when you're applying the variational method. Okay, so let's start by defining this quantity that I call h bar. It's not normal h bar, it's big H bar. Okay, so it's the Hamiltonian. It's the expectation value of the Hamiltonian with respect to these trial kets. Okay, and here we're accounting for the fact that our guess our guess or our trial kets aren't necessarily normalized. So we want this thing to be, to have the correct normalization. So I've put the normalization down in the denominator. Okay. All right. So the theorem goes like this. Okay. So it says that irregardless of our choice of a ket, right? I can pick whatever ket I want, irregardless of the form. When I go and plug our guess in here, compute it with the Hamiltonian that's given, I am guaranteed that it will always give me an upper bound. In other words, we'll never underestimate the ground state energy. We'll always overestimate it. Okay. The equal sign here is if we were extremely lucky and we guessed precisely the exact form of the true ket or the true wave function. Okay, and we'll see. I'll show you a case where we do that. Okay, and you'll see the equal sign come in. Okay, so this is a cool theorem. I mean, it's telling us that irregardless of however we choose the ket, whatever form, doesn't matter. We're always going to overestimate the ground state energy, never underestimate it. Okay, so let's keep that in mind. All right, and what I want to do actually is prove this theorem. Okay, you guys know I don't like to usually prove stuff, so if I'm doing a proof, it's got to be cool. All right. Okay, so what we're going to do is we're going to start with a trial ket. Okay, and we know that the Hamiltonian has exact solutions. We just don't know what those exact solutions are. But just like any quantum system, we know that these kets form a complete set, a complete basis, right? So what we can do is let's take our trial ket and multiply it by 1, okay? And multiply by 1 in the form of the completeness relation of the true kets of our Hamiltonian, okay? So this is just the normal trick we're doing. We don't know what these things are, but we know that they form a complete basis, okay? Oops, all right. Okay, and so like I said, we don't know what these guys are, but we do know they're eigenkets of the Hamiltonian. So when the Hamiltonian hits this guy, it'll give me some energy eigenvalue back times the original ket. Okay. All right. So let's take this expanded form of the trial ket and plug it into our definition for big H bar. Okay. So let me do that, and I have to be careful. Remember, I have to be careful that when I'm summing over these indices, I don't want to use the same indices for each of the or for any of the kets or the bras. So I'm going to use 3 different dummy indices. So I'm going to use one here that I call L, one here that I call K, and one here that I call M. okay? And so I've plugged those in, okay? Now I've got, in this middle here, I've got a matrix element that now I know how to evaluate, right? I know that the Hamiltonian, when it hits one of its eigenkets, it's going to give me the eigenvalue back. And these guys, K and L, they're orthonormal, right? So that's going to give me a delta function in K or L. And so that'll collapse one of these sums, okay? So that's what I've done here. I've collapsed the L sum, okay? And now I've changed this L to a K from the delta function. And now this thing is just the complex conjugate of that. So I can rewrite the product of those two as the complex conjugate squared, right? And times the energy eigenvalue that came out of the Hamiltonian hitting this guy. Okay? All right. So now what I can do is use a little trick. Okay, so I've got something that looks like this. I can't really cancel these guys out because there's going to be when you sum over these terms, the denominators aren't going to cancel, right? Especially with this energy term here, or in particular with this energy term here. Okay, so what I can do here is let me add and subtract the ground state energy. Okay, so and going from this part to here, that's what I've done, right? So I've taken the energy and I've added and subtracted the ground state energy. Okay, so what does that let me do? Well, what it does is it lets me take this term right here, the plus E naught, the plus ground state energy, multiplied times this, divided by that, right? And then the other piece, right? But let's concentrate on this first piece, okay? So this piece hitting that, this thing doesn't depend on K, right? So I can pull it out in front, and now the numerator and the denominator cancel each other, okay? So that term is going to leave me with a term that looks like this, E naught, plus the sum of the other stuff that's left over, okay? And by definition, these things, are greater than zero, right? They're basically probabilities, so they have to be greater than zero. And here, E sub k is some energy that's above the ground state energy, okay? So that means that the difference between Ek and E0 is greater than zero. And so this second term is positive definite, okay? And so what it's telling us is that this H bar quantity, irregardless of what we choose for our trial ket, is always going to be greater than or equal to the ground state energy. Okay, and like I said, the equality sign only holds if our trial ket exactly coincides with the true wave function. Okay, and what this inequality does is it gives us a way, in principle, to determine the ground state energy and the eigenket, right? So if we make this guess for the eigenket, and we go and we compute the trial ground state energy, our guess for the ground state energy, and we see that our ground state energy that we computed from this guess is pretty close to the experimental value, then that gives us some confidence that in our guess for the eigenket or the wave function. Okay, so I think let's see where I'm gonna go. Yeah, let me stop. Well, here, just give me a couple of minutes and we'll get to a good stopping point. All right, so this is just like class, okay? All right, so so now we have an approach, okay? So we can, if you think about it, we could systematically just keep guessing wave functions, right? And just tabulate the results for, our guess of the ground state energy, right? And then pick the lowest or pick the one that's closest to the true ground state energy. It would be the lowest one, right? Because all of our guesses are going to be upper bounds, right? So, so we could do it that way, right? But if we wanted to do it in our lifetime, we could be a little smarter about it, right? Instead of doing all these guesses, and the way to do that is to introduce some parameters into your guess, okay? And then what you do is you try to optimize these parameters, or to minimize the value of the ground state energy that you compute, okay? So now not only are we going to just guess some wave function, but we're going to parameterize it with some parameters. And we'll typically start with just one parameter and see how we do. If we get really close, we call it a day and go home and be happy with ourselves. If we're not that close, then we can try tweaking it by putting in another parameter and so on and so forth, okay? So the Hamiltonian, or the H bar, this guess for the ground state energy that we'll compute, is going to be a function of these parameters, okay? So it might be 1, 2, or 3 parameters. I don't think we'll ever get to 3. We might get to 2, okay? All right, and like I said, what we'll do is we'll minimize, we'll go through a minimalization process to try to find the values of alpha and beta that minimize the value that we would guess for the ground state energy, okay? And like we said, we always know that regardless of how we compute this guess of a ground state energy, we always know it's going to give us an upper bound, okay? All right, but the name of the game, really, when you're using the variational method, is finding the lowest upper bound for a reasonable amount of work, right? So you could keep on if you wanted to. If you really, wanted to punish yourself, you could keep tweaking this, guess for the wave function, add on more parameters, tune the parameters, do all this stuff, and, only gain, fractions of a percent, and at some point it just doesn't become worth the effort, okay? So let me just summarize the recipe real quick for the variational method, and then next time we'll actually start to apply it to some cases, okay? So the variational method recipe is very nice and compact, and that's why a lot of people like it, because it's like a step-by-step process, and it's very hard to screw up, okay? So the first thing you do is guess. Right, you guess a trial ket, or you guess a trial wave function, okay? And when you do this, you want to, to save yourself some work before you go off and willy-nilly pick some wave function and, start computing, use your physical intuition, okay? We'll see examples of this next time, okay? But make sure you really think about it before you go off and just try to calculate with whatever trial ket, comes to mind, right? So you pick your trial ket. In our first couple of cases, we won't parameterize these things, but you can optimize your choice by including some parameters, right, into the trial ket. And then once you compute this H bar, it's going to be a function of those guys, okay? But then we want to minimize. But then we can use these guys to minimize the value of H bar. And the way we do that is by taking derivatives with respect to these parameters that we introduce, and we set them to 0, and then we solve, whatever these system of equations are, and find the optimal values for lambda 1, lambda 2, so on and so forth, that minimize H bar, okay? And that's how we find the optimal values, and then we'll plug those values back in, and that will give us the lowest possible value for H bar, given however many parameters that we plug in, okay? All right, so next time we'll take this variational method and we'll apply it to a couple of simple examples that we actually know the solutions to, okay? So one will be the particle in a box, okay? And this is typically what you do when you write down a model or you come up with some new calculational method, is you want to apply it to a case that you know the solution, right? Even though it's built for problems where you don't know the solution, okay? So we'll use this to compute the ground state energy of a couple of familiar cases, and this we'll see will give us some confidence in the variational method itself. Okay, all right, so that's it. I'll put together a Dropbox with these notes, the syllabus, and I'll start to look and see what kind of homework problems I have to put together. All right. Okay. Well, I appreciate everybody, dealing with this. It's, like I said, it's not ideal, but we'll get through it. Okay. And if you ever have any questions, don't hesitate to call me or, well, to email me. Okay. Have a good one.